The next quantity I'll talk about is displacement and strain. So displacement. So what is displacement? It's basically how far something moves. I have a mass sitting on the ground. I apply force, and in the next instance, it moves here. What's the displacement? Here to here. This is the displacement, which I'll call D. There's so many different denominations, so many different types of symbols that can be used for displacement. Sometimes it's U, sometimes it's just different stuff. So don't bother about the symbol yet. But anyways, you move this block and then you let the force go. Then you say the force equals 0, and then it just, the block stops moving and you end up with a displacement. Okay. So now let's consider a spring. You have such a spring, and let's say you have a nice area by which to apply the force. So we know in the case of a spring, force equals the spring constant times the displacement. How far the spring moved. I think it's usually negative. I can't remember on the top of my head. Or can I? Anyway, so you displace it. If you displace the spring this way, the spring's going to push back. So therefore, it just all depends on which kind of signs you're using. So then force equals the spring constant times the displacement. So then, yeah. So again, the physical dimension that it moves in is the force, which is going to result in this case. But now let's take a look at the other side of the coin. We have strain. So this is probably a word you got introduced to if you took a mechanics of materials course. In that case, you'd be considered this quantity called strain. And strain is a non-dimensional quantity. It's basically telling us the relative displacement relative to the entire size. And I'll explain what that means now with regards to a spring. But we're not going to use a traditional, physics 1, college physics 1 or, introductory physics type of spring. We're going to be using a material. So let's say we have a block of, I don't know, let's say call it copper maybe, or steel. And it's attached to a wall. And what we're going to do, we're going to push on it. It's a force. Oh, and forgot it has length L. And do we push on it with the force? It's a real bar, so you can actually have to push on it with a stress times an area. But we know the stress. Let's say we know the area, so we get a force. Okay. And this bar deforms. Obviously, it shrinks, right? This bar becomes smaller. And because this bar becomes smaller, it displaces. So there's a displacement going on here. We'll call it D. Okay. And the new size of the bar, it changed D. D is the total change of the size of the bar. The original size was L. The new size is L minus D because we shrunk it. Or you could have pulled it the other way, and then we'd get L plus D. It doesn't make a difference for this explanation. So we get something else. So what is strain? So strain is actually denoted as X, like this, like curvy X, a little bit. When you're handwriting it, the computer is probably gonna be like a little lowercase x, but we'll draw a little curvy, nice X. There you go. So what is strain defined as? It's a non-dimensional quantity defining the relative amount of displacement. So we have D over L, and this is strain. So the displacement over the length And right, we have units, meters over meters, it cancels out and doesn't have units. A lot of times you'll see units because the strain is often really small. It's often like some number times 10 to the minus 6. We often denote strain as, this is a strain, let's say that number. We often denote it as micro. But again, you don't say like 20 micro. You say 20 micrometer over a meter. So these cancel out. This is just like a traditional way of writing strain. You write micrometers over meters. The meters cancel out, and you just left with micros. And you realize that this stands for a 10 to the minus 6. So that was strain. So we covered both strain, displacement. We covered stress and force. So these are like kind of like the strain is like the real thing that is happening to the actual material, and this is how we're making that transition from these point mass, these point diagrams, these free body diagrams until actual real material properties, which are non-dimensional. So oftentimes we'll find material properties relating non-dimensional type of quantities. For example, not exactly non-dimensional, but for example, I mentioned rho, which the mass density is kilograms per meter cubed. So this could be applied, for example, if we have a steel bar. It doesn't matter what shape of the steel bar it is. As long as I know the shape, I can calculate the mass because I have the volume. But if we have the mass, okay, we have a mass of a steel bar, it's not a property of the material. It's a property of that piece of steel I have. It's not a material property. So this is a important thing to understand, the difference between a material property and a property of the sample or the sample of material you have in front of you. They're two different things, and we have to realize that. Just like force and stress and strain and displacement, these all have these different ideas to them. So next we'll talk about the Young's modulus.